This video will cover the function section of the AP Math syllabus. The best way to go through this section is I'm going to go through 4 examples, each with a slight difference and pointing out some key areas of focus within this section. The first example is if you've given a simple cubic graph, which you will get to see in core maths for grade 12. F of x is equal to x cubed minus 3x plus by 2, and you asked to sketch the graph. The first thing you should be doing is working out your intercepts with the axis. I like to start with the y-intercept because it's the easiest. So you start y-intercept, you're obviously making x equal to 0. You sub in 0 into x's place and you'll get the y-intercept to be 2. So your coordinates of your y-intercept are obviously 0 and 2. Then if you go to your x-intercept, you're making y equal to 0. So you're making the equation equal to 0. You factorize out and you come to see that x equals minus 2 or x equals 1. Just an important side note, you'll see I've made a note of it here in yellow. If you get a bracket that is squared, you know that because of the squared bracket, you know that a turning point will also occur at this point. So there will also be a stationary point at x equals 1. Then if we look, the second step we need to look at doing is our stationary points. We obviously find the derivative of the equation. Derivative of the equation is f dash x is equal to 3x squared minus 3. Obviously for stationary points the gradient is equal to 0, so we make the derivative equal to 0 because the derivative is obviously the gradient. And we find that we have stationary points at x equals 1 and x equals minus 1. Then all we do is we sub those points back into our original equation to find our relevant y values, and we get those y values to be at 0 and 4 respectively. Then what we do is, what I like to do is obviously draw in dots where you have found points, and then you simply just connect the dots, obviously knowing that you have a turning point at x equals minus 1 and a turning point at x equals positive 1. Then if we move on to the next example, obviously getting slightly harder, although this can still be considered a hyperbola. It's important to note that there are only vertical and horizontal asymptotes when the exponent in the numerator is smaller than or equal to, as in this case, to the exponent in the denominator, i.e. there are no oblique asymptotes. First things first, obviously look for your intercepts. For your y-intercept, you're making x equal to 0. You sub in 0 into x's place, and you get your y-intercept to be at 0. Obviously sub that back into your original equation, and you get your coordinates of the y-intercept to be 0, 0. Just as another side note, if you get y equals to 0, as I've highlighted in light pink over here, you know that it automatically goes through the origin. Then when looking at the x-intercept, you're obviously making y equal to 0. So you're making the equation equal to 0, and you also find that x is equal to 0, so your x-intercept is also the origin. Then your next thing is obviously your stationary points, so you find the derivative of your function. In this case, we used the quotient rule, as you can see here. You obviously make your derivative equal to 0 to find your stationary points, but in this particular case, you see that we have no solution for x, so you can immediately deduce that there are no stationary points present on this graph. The third point, and we haven't seen this before, is finding your vertical asymptote. Always when looking for a vertical asymptote is where your denominator is equal to 0. So my denominator in this example is x minus 1, so I make x minus 1 equal to 0, and I find that there's a vertical asymptote at x equals 1. Then I look at my horizontal asymptotes. My horizontal asymptotes always is the limit to infinity of the equation that we're given. And if we simplify that, obviously divide through by your highest power, etc., we get our horizontal asymptote to be at y equals 1. Then in terms of sketching the graph, what I like to do is, obviously, if they haven't given you the axis, to sketch the axis. And although it takes up a lot of time, I find drawing the axis to scale is very helpful. Then the next thing that I always do is draw in my asymptotes, and because I know there's no stationary points, and before I get to that, I also draw in all the dots all the points that I have. So obviously I have my x and y intercept at the origin. Then I simply just join the dots, or else draw in a hyperbolic function, as you can see in this graph. Then if I move on to the third example, getting a bit more complicated, this one will not necessarily look like a hyperbola. We have minus 8 over x squared minus 4. Don't panic. First things you do is look for your intercepts, your y-intercept. You're making x equal to 0. So you're saying you're subbing 0 into x's place, and you get y to be 2. So you know your y-intercept is at 0 and 2. Then your x-intercept, you're making y equal to 0. So you make the equation equal to 0. And you get minus 8 is equal to 0, which cannot work, no solution. And you can immediately deduce that there are no x-intercepts on this graph. Then if we're looking at stationary points, we're obviously finding the derivative of our function, which again is using the quotient rule. That's why it's important to understand your quotient, product, and chain rules before attempting any of the application type questions. You make your derivative equal to 0 to find out where the gradient is 0, and you'll eventually find out that you have a stationary point at 0 and 2. Obviously, once you find that 0, just jumping back a step, you sub the 0 back into the original equation, not into the derived equation, back into the original equation to find that corresponding y value to be 2. Then we look at our vertical asymptotes, obviously where your denominator is equal to 0. So we take our denominator of x squared minus 4, make it equal to 0, and we find vertical asymptotes at both x equals 2 and x equals minus 2. Then our horizontal asymptotes, we're making a limit to infinity of the sum, and we eventually work that out to be 0. So we have a horizontal asymptote at y equals 0. Then for this particular graph, you need to work with shape. And I've done it very simply here. But you can, firstly, what I would recommend is that you obviously find out if your stationary point is either a local maximum stationary point or a local minimum stationary point. I haven't included that step in my working because I know that you guys will be able to work that out. But what I also like to do is just find out my gradient. So I take any point smaller than minus 2, sub it back into my derivative, which is my gradient, get a negative gradient. Then I should have included the point 0 here, because between minus 2 and 0, as you can see on the graph, you've got a negative gradient. And between 0 and 2, you've got a positive gradient. And then again, between any number bigger than 2 will yield a positive gradient, which I haven't included, however, a negative y value. And that all just comes from subbing in values either back into your original equation to see whether y is positive or negative, or to see whether the slope using your derivative is positive or negative. Then the fourth and final example, which is one of the hardest examples you'll get, is when you're including an oblique asymptote. So if you give an f of x is equal to x squared minus 3 over 2x, sorry, that's an imaginary 1, so 2x minus 4, you immediately can tell oblique asymptotes occur if the exponent in the numerator is larger than the exponent in the denominator. So I've got x to the 2 in the numerator, x to the 1 in the denominator. So I must know, okay, cool, I'm definitely going to get an oblique asymptote coming out of this. And then another very important note is that there are only vertical asymptotes when there's an oblique asymptote. There are no horizontal asymptotes with oblique asymptotes. Obviously, first things first, find your intercepts. Y-intercept, make x equal to 0. Y, sub in 0 into x's place, you get y at 3 over 4. That is your y intercept coordinates. Then your x-intercept, you're making y equal to 0, which is just making your equation equal to 0. And you can solve your x-intercepts to be plus or minus root 3, which comes out to about 1.7. Then if we look at our stationary points, we're obviously finding the derivative again using the quotient rule, making our derivative equal to 0 because we want to find where our gradient is equal to 0. And we can solve through eventually simplifying to get our stationary points at x equals 3 and x equals 1. Sub those points back into the original equation and you can find your coordinates to be 3 and 3 and 1 and 1 respectively. Then if we look at our vertical asymptote, is where our denominator is equal to 0, so we take our denominator of 2x minus 4 and make it equal to 0. Solving that, we get a vertical asymptote at x equals 2. Then usually our fourth step is to look at our horizontal asymptotes, but because we already know that the exponent in the numerator is larger than the denominator, we can skip that step because we know there aren't any, but we have to now look for an oblique asymptote. And what an oblique asymptote essentially is a straight line that runs through your graph that forms an asymptote. So there is two ways of working this out. A very common way, which a lot of schools teach, is the long division method. However, there is an easier method, which is the one I will show you, and I strongly encourage that you use this method because it can save a lot of time, especially in a time pressured situation. So how this works, now this part you really have to focus. Whatever's in your numerator, so x squared minus 3, you put to the left hand side of your equal sign. Then you obviously put an equal sign, and whatever's in your denominator you put as your first bracket, and then you simply write another bracket with mx plus c. Repeat that step. Drop down your numerator is equal to your denominator, so numerator, denominator. Then what you must do is you must work out what you need to times this bracket by in order to get it to this bracket. So you first look at your x squared terms. What do I multiply 2 by? What do I multiply 2x by to get 1x squared? Obviously 2, you work out that you need to multiply it by a half x, because 2 times by 2x multiplied by a half x is equal to x squared, so you've satisfied that. Then you move on to looking for the x terms. Obviously in this particular equation there is no x term, so you've obviously now got this half x, so you work out minus 4 multiplied by half is minus 2x. So how am I going to get minus 2x to cancel out? I need to plus the 2x. So minus 2x through these two ones close to each other, and then plus 2x, which cancel each other out to leave us with no x. Now you might be thinking, why the hell this isn't working? I've got minus 4 times 1, which is minus 4, not minus 3. So you simply add in your remainder at the end, outside the brackets. But this is very helpful because whatever this bracket is your oblique asymptote. So we have an oblique asymptote at a half x plus 1. Then we simply find out the shape of our graph using the derivative. So we take a point, any point smaller than 1, we find that the gradient is obviously negative. We take a point between 1 and 2, we find the gradient, a point smaller than 1, the gradient is positive. Then a point between 1 and 2 we get to be negative. Between 2 and 3 any point will be negative in terms of the gradient, and bigger than 3 will be positive in terms of the gradient. Then all we do is we put in our relevant points with a dot. So here we put in our two stationary points at 1 and 1 and 3 and 3. We know there's going to be a turning point there. If you don't like this method, you can also use obviously the double derivative to find out whether it's a max or a min turning point, but this method works well. You can see you've got a positive gradient here, so then you draw a line with a positive gradient till you hit your turning point, and then it goes from a negative gradient from x equals 1 to x equals 2, which is your vertical asymptote, and then you climb to the right of your vertical asymptote. You can see between 2 and 3 you've got a negative gradient as shown here, and bigger than 3 you've got a positive gradient as shown here. Then you can simply add in your x-intercepts, which is here and here, and your y-intercept. And obviously when you're sketching your asymptotes, always include the equation. So x equals 2 and your oblique asymptote at y equals a half x plus 1. Thank you. That concludes the video on functions related to the AP Math syllabus.